Greetings and welcome to lesson 9.5. Let's wrap up this chapter by working through a few examples using the full process of hypothesis testing. Before jumping into several walkthroughs of hypothesis testing, I just want to talk a little bit more about some information and reiterate some information that we will want to be aware of. One is you will see level of significance as a percent or preconceived or preset alpha. Those are all regarding alpha, and just be sure that you translate any percent of levels of significance over to a decimal to use. When you are actually running hypothesis tests, let's say you're in a psychology class in your bachelor's degree and you have to gather some information, you have to run a hypothesis test on some claim that you want to make. It is a good practice to select your value of alpha before collecting your data. If you select your alpha after you've collected your data and run some numbers, you may have just manipulated the end result of your test by selecting your level of significance after. So maybe before the test, you would have selected a 0.1. And after the test, if you're looking at your numbers a little bit, maybe you select a 0.01. In one instance, your test might fail. In the other instance, your test might not fail. Because of the possibility of manipulating the outcome, it is always better to select your level of significance before you even go after your data, before you collect your data. If no level of significance is given, just use a common alpha 0.05. Hypothesis tests are left, right, and two-tailed, and it's the alternative hypothesis which tells you which type of test that would be by the symbol it has in there. Remember, an HA only has symbols of less than, greater than, or not equal to. And it's that symbol that's going to give away that little clue as to if it is left, right, or two-tailed. When setting up a problem, it's amazing how much information you can get out of a simple statement. Let me give you a statement. H0 is mu is greater than or equal to 5, and HA is mu is less than 5. Here's what I can get out of that small a bit of information. Number one, the test is a single population mean. Now, I don't know if it's going to need a z-test for population mean or a t-test for population mean, but I do know I'm going to run a test for a single population mean. HA tells me that it is a left-tailed test. And the dealing with the mu, I know the mu for the population is 5. So I can kind of sketch out what my graph will look like. So by that small bit of information, we know that it's a test of a single population mean. HA tells us it's a left-tailed, and we can sketch a graph using 5 as our mean. What about H0? Where P is less than or equal to 0.2 and HA, P is greater than 0.2. Well, here we're not dealing with mu anymore, we're dealing with P, meaning a proportion. So this is a test of a single population proportion. And HA tells us this test is a right-tailed test. It's pointing, that arrow is pointing to the right. We know our proportion is 0.2, so we can sketch a graph of what this problem looks like. We don't have the exact p-value, but at least we can sketch that it's a right-tailed test. Another scenario, H0 is mu equals 50, and HA is mu does not equal 50. Okay, we're back with mu, so we know this is a test of a single population mean. And our HA is not equal to, so therefore this is a two-tailed test. So when we're graphing this or sketching an idea of what this problem looks like, we're going to have two tails with mu 50. Now we don't have all the details, we don't have the test results, but setting up the problem is gathering information out of the problem description. And by your H0 and HA statement, you'll know, at least if your test is a mean or a proportion test, and HA will tell you if it's a two-tailed, a left-tailed, or a right-tailed test. Here's our problem description. Jeffrey, as an 8-year-old, established a mean time of 16.43 seconds for swimming the 25-yard freestyle with a standard deviation of 0.8 seconds. His dad, Frank, thought that, well, Jeffrey could swim the 25-yard freestyle faster using goggles. Frank bought Jeffrey a new pair of expensive goggles and timed Jeffrey for 15 25-yard freestyle swims. For the 15 swims, Jeffrey's mean time was 16 seconds. Frank thought that the goggles helped Jeffrey swim faster than the 16.43 seconds. Let's conduct a hypothesis test using the preset alpha equals 0.5. And we're going to assume that the swim times for the 25-yard freestyle are normal. The first thing we really need to do is set up our hypothesis test. When I mean set up our hypothesis test, we need to pull out the information from the problem that we're given. We need to state our hypotheses, meaning our H0 and our HA. We need to figure out which one of those is our claim. We need to identify alpha, and we need to determine the distribution and the type of test that we're going to run. Now, going through the problem, we know that there is an established mean time of 16.43, meaning mu is 16.43. We also know that the standard deviation is 0.8. That is for the population, so it's sigma equals 0.8. For 15 swims, so those are the trial runs of 15 swims, so we know our N value is 15. His mean time was 16 seconds. That 16 seconds correlates with the sample, and therefore that is our X bar. So our average for the sample, X bar, equals 16. And then lastly, our alpha is 0.05. Frank thought that the goggles helped Jeffrey swim faster than 16.43 seconds. Faster means that their time is less than the 16.43. So the claim is that Jeffrey's trial times are less than 16.43, so this is an HA. So HA is mu is less than 16.43, and our H0 will be mu is greater than or equal to 16.43, and our claim is the HA. Now, putting all this information together, we have a mu, we have a sigma, we have our H0, we have our HA. This is a normal distribution where standard deviation is known, and therefore we're going to do a z-test for a single population mean. For the next step, we're going to calculate our test statistic, our z-score, and then we're going to find the corresponding p-value. Because this is a z-test, our z equals x bar minus mu, all divided by the standard deviation divided by square root of n. Plugging in all of our values, we get 16 minus 16.43, all divided by 0.8 divided by the square root of 15. We get a z-score of negative 2.0817. Now that I have my z-score, I am going to use the website to find my p-value from my z-score, but I also want to know what type of test this is, if it's a left-tailed, a right-tailed, or a two-tailed. Looking at HA, our symbol is less than, and that's pointing to the left, and therefore this is a left-tailed test. Plugging in my z-score, saying that it is a left-tailed test, I get the p-value of 0.0187. Now it's time to use this p-value and the decision rule to make a decision regarding H0. Our p-value, 0.0187. Our alpha is 0.05. Our p-value is less than alpha, and therefore we need to reject H0. And because we are rejecting H0, That means HA is good. HA is our claim, so our claim is good. Now we need to translate all of that into our conclusion. At the 5% significance level, we conclude that Jeffrey swims faster using new goggles. The sample data has shown there is sufficient evidence that Jeffrey's mean time to swim the 25-yard freestyle is less than 16.43. A shorter way of saying this is because our claim was an HA and we rejected H0, there is enough evidence to support our claim that Jeffrey's mean time is faster using the goggles. For walkthrough 2, we have statistics students believe that the mean score on their first statistics test is 65. A statistics instructor thinks the mean score is higher than 65. He samples 10 statistics students and obtains the scores of 65, 65, 70, 67, 66, 63, 63, 68, 72, and 71. He performs hypothesis testing using a 5% level of significance. The data are assumed to be from a normal distribution. First things first, let's set up this hypothesis test. We've got to pull out the information we know, and there is some information we're going to have to calculate. What is the mean? The population mean, we're going to be testing against 65. The mean score on their first statistics test is 65. What is our standard deviation of the population? Nowhere in the problem does it give us our standard deviation for the population. So right then and there, we should know we're going to have to run a t-test. So we have the mean, but we don't have the standard deviation, so we've got to run a t-test. We do know our sample size n is 10. And if we throw those values into a calculator and add them up and divide by 10, we get the x-bar, the mean score, of 67. Now I'm going to use technology to find the sample standard deviation. And when I do that, I get S equals 3.1972. Our alpha is 5%, so 0.05. And because we're going to run a t-test, we also have to know the degree of freedom. Degree of freedom is our n-1, so our degree of freedom is 9. So we know from the description of the problem that the instructor thinks that the mean score is higher than 65. And if the mean is higher than 65, that means the mean is greater than 65 in math language, and therefore that is an HA. Our corresponding H0 will be mu is less than or equal to 65. And our claim is the HA. So now that we have all of our information pulled out of the problem set, we know our H0, we know our HA. Looking at our HA, we have a one-tailed test. In fact, it's a one-tailed, right-tailed test. We can figure out what our test statistic, our t-score, is. And once we find our t-score, we can translate our t-score into a p-value using a website technology. The equation for t is t equals x bar minus mu all over the sample standard deviation divided by the square root of n. So equation for t is pretty much exactly like z, except instead of using the population standard deviation, we're using the sample standard deviation. Plugging in all of our values, we get 67 minus 65, all divided by 3.1972 divided by the square root of 10, and that equals 1.9782. Taking this t value and our degree of freedom, I'm going to plug it into a website to calculate our p. It's important to know if it's a one-tailed or two-tailed because the values are going to be different depending on if it's a one-tailed or two-tailed. Our p value for a one-tailed is 0.0397. Now that we have our p-value, We can use this p-value to make a decision regarding H0. Our p-value is 0.0397. Our alpha is 0.05. Our p is less than our alpha, and therefore we reject H0. The good news is, even though we're saying our H0 is bad, we're rejecting it. That means our HA is good, and our claim was an HA, and therefore our claim is good. Putting that all together, we're going to make a conclusion that at 5% level of significance, the sample data show sufficient evidence that the mean average test score is more than 65, just as the math instructor thinks. Let's go through yet another walkthrough. I'll call this walkthrough number 3. June believes that 50% of first-time brides in the U.S. are younger than their grooms. She performs hypothesis testing to determine if the percent is the same or different from 50%. June samples 100 first-time brides, and 53 reply that they are younger than their grooms. For the hypothesis test, she uses a 1% level of significance. Let's set up the problem by grabbing all the information that we can, determining what distribution we have and what type of test we're going to run, and let's set up our H null and HA. June believes that 50% of first-time brides in the U.S. are younger than the grooms. That's a proportion. And immediately, since we're dealing with proportion, we should recognize that we are going to have to use a z-test for a single proportion. So now that we know what type of test we're going to use, that will help us figure out what all the information we're going to need to have. Because the z-test for a single proportion is z equals p prime minus p, all divided by the square root of p times q all over n, we're going to need p prime, we're going to need p, we're going to need q, and we're going to need n. Those are the values that we're going to have. There may be more values we'll need to actually calculate these things, but those are the values we need to actually run the test. So let's take these one at a time. Our p-value is the 50%. So in decimal, that's 0.50. Q, we can calculate by 1 minus the p-value. And 1 minus 0.50 is 0.50. So our P is 0.50, our Q is 0.50. Our N is the sample of 100 first-time brides, so N equals 100. We have to figure out P prime. Now P prime are the yes replies from those she sampled. So 53 replied that yes, they're younger than their grooms out of the 100. So 53 out of 100 would be our P prime of 0.53. I'm going to figure out if she performs the hypothesis test to determine if the percent is the same or different. Because it's not explicitly stated, it really is up to you which one you choose, either an H0 or an HA, to have to be your claim. But ultimately, your conclusion has to be based on the result of your test and which one you selected for the claim, or you need to word it in such a way that there's no ambiguity. I'm going to choose to have my claim be HA. So now that I'm going to say my claim is let's see if the proportions are different. We can set up our H0 where P equals the 0.50, and our HA would be P does not equal the 0.50. Now let's run our z-test. So we have z equals P prime minus P all over the square root of P times Q divided by N. Plugging in all of our values, we get 0.53 minus 0.50 divided by the square root of 0.50 times 0.50 divided by 100. All of that equals 0.06. Now, using technology, I'm going to take this z-score, plug it in to an online calculator and make sure that I have two tails selected. And I get the p-value of 0.5458. Now that we have our p-value, we can make a decision regarding H0. Our p-value is 0.5458. Our alpha is 0.01. Our p-value is larger than our alpha. So p is greater than alpha. So we do not reject H0. Because we do not reject H0, we can word our conclusion that at 1% level of significance, the sample data do not show sufficient evidence that the percentage of first-time brides who are younger than their groom is different from 50%. We don't have sufficient evidence to show that it's different than 50%. So in essence, we can't reject H0, so our claim that it is different is bad. All right, let's quickly run through a hypothesis test from start to end. This shouldn't take too long, but I do want to stress that a lot of the work can't be done on a calculator. It has to be done by you to understand what you need in the beginning. Then you can use the calculator, and then you have to figure out what's happening in the end for the conclusion. So the calculator will only do the math. It's not going to make the decision for you. And it's not going to tell you which test to do. So let's read through a problem. From generation to generation, the mean age when smokers first start to smoke varies. However, the standard deviation of that age remains constant of about 2.1 years. A survey of 40 smokers of this generation was done to see if the mean starting age was 19. The sample mean was 18.3. Now that's all the information we're given, except we want a confidence level of 5%. So we're going to use alpha of 0.05. But what type of test are we going to use? There's kind of three that we've been focusing in on. A z-test for the mean, a t-test for the mean, and a z-test for proportion. Well, we don't have proportions here, so we can rule out the third one. If we use a z-test, that means we have to have the standard deviation of the population. If we need to use a t-test, we don't have the standard deviation of the population. In this case, we do have the standard deviation, so we'll be using a z-test. Now let's figure out what our H0 and H alternative is. A survey of 40 smokers of this generation was done to see if the mean starting age was 19. Is means equal. So this claim is an H0. Our mu equals 19. So H0 is mu equals 19. Our H alternative, HA, is going to be mu does not equal 19. And H0 is our claim. So whatever result happens actually happens not only to H0, but it's also our claim. So if we reject H0, that means we have to toss out our claim. It's no good. If we fail to reject H0, that means our claim is good and we can't toss it out. Okay, now that we know what type of test, let's go ahead and run the test. So I'm going to go to Stat, Tests, and run a z-test. Now we have stats and not data. I don't have a list of data, so I'm not going to use that. I will use stats. Our mu naught is the 19. Our sigma is 2.1. Our X bar was 18.3, and our N is 40. Now we do have to decide what our HA was, so that's why we ran through that before we even hit the calculator. And because H0 is equal, our HA is not equal, I want to make sure that the not equal is highlighted. And because I can, I'm going to go ahead and draw it, because that not only will get calculated and give us our p-value, but it will give us a nice picture as well. Perfect. Because H0 is an equal, it is a two-tailed test, and our p-value is 0.035. we're comparing that to our alpha value of 0.05. Our p-value is less than our alpha, and therefore we have to reject H0. And because H0 was our claim's no good. So there is enough evidence to reject our claim that the mean age of the starting age of smokers is 19 for at least this generation. So if P is less than alpha, we reject H0. Our claim is H0, so we have to say our claim is bad. We just have enough evidence to reject our claim. All right, that's it for this time. Until next time, be seeing ya. Let's work through a problem from the top down. There's a lot of information that we're going to have to get out of the problem before we even touch the TI-84 plus. So let's read through the problem. The National Institute on Standards and Technology provides exact data on the conductivity properties of materials. Following are the conductivity measurements for 11 randomly selected pieces of particular type of glass, and our data is provided. Is there convincing evidence that the average conductivity of this type of glass is greater than 1? And we're going to use a significance level of 0.5. Let's assume the population is normal. Now, the first thing I want to do is I do want to clear out my L1 and my L2. I'm not going to be using L2, but I just want to make sure that these things are clear just in the event that there's some erroneous data in there and I don't want it to affect my numbers. Now that I've cleared out my list, I'm going to go to Stat, edit my list, and enter my data. I just want to make sure that I have 11 points in there. Yes, I do. Now it's time to run the test. But which test do we use? Do we use a z-test for mean? Do we use a t-test for mean? Do we use a z-test for proportion? The TI-84 plus isn't going to tell me which test to use. I have to get that out of the problem description. To use the z-test for means, I have got to know the population standard deviation. And nowhere in this problem does it tell me what the standard deviation of the population is. So that rules out that test. The z-test for proportion, well, we're not given proportion. We're given raw data. So again, that rules out that test. But before you jump to the conclusion that, oh, it's the t-test for the mean that I have to do, how do we know? Well, we are not given the standard deviation. So that's a clear clue that the test that we need to do is a t-test. So tests are under stat. Run over to tests, down to t-test. Now my input is not stats, it's data. So I'm going to go ahead and click on data. My mu 0 is what is the average conductivity of this type of glass. Is it greater than 1? So my mu 0, my initial mu is 1. My list where my data is L1, so I'm going to keep that the same. My frequency is just 1. I don't have a frequency table. If I did, I would put in like L2 here. And then my mu is dependent on my H alternative. What is the symbol for our H alternative? Is there convincing evidence that the average conductivity of this type of glass is greater than 1? So my HA will be greater than. So the first one is not equal. Second is less than. The third one is greater than. So I hit enter to make sure it stays on there. I am not going to draw this out. I am just going to calculate it. But if you wanted to see it drawn out, you can click on draw. Now I'm going to calculate. Okay, my test is mu is greater than 1. My t-value is 2.0138. My p-value is 0.0359, and it gives me my average for my sample, my standard deviation for my sample, and my n value. Now, it ran all the math in the background, but I personally have to come up with my decision. we are comparing our p-value to our alpha value. Our p-value is 0.0359. Our alpha is 0.05. Because our p-value is less than the alpha value, we must reject the null hypothesis. So it's reasonable to say that our data supports the claim because our claim was actually an HA. A lot of doing the t-test and the z-test and the z-test for proportions is not going to be taken care of by the TI-84. The TI-84 will run the numbers, but ultimately you have to interpret the data. Now, if you were curious, let's go back to stat and to the test, and let's go down to our t-test, and instead of calculate, everything else stays the same. I'm going to go ahead and draw this so you can see what it looks like. Okay, so there's our graph, and we are still given our t-value and we're given our p-value. So if you were curious as to what the shading effect is for these tests, you can certainly click on draw instead of calculate. The important value is the p-value because that's what we want to compare to alpha. And again, since our p-value is less than our alpha, we're going to reject our null hypothesis. Our original claim was an HA, and therefore we have enough evidence to support our claim. Okay, so that's it for this example. Till next time, be seeing you. Let's work through a hypothesis test problem from top to bottom. So here's the problem we have. In a study of 420,019 cell phone users, 172 of the subjects developed brain cancer. We want to test the claim that a cell phone user develops brain cancer at a greater rate than that for a non-cell phone user. And we know the rate of brain cancer for non-cell phone users is 0.0340%. Now, since this is a very critical issue, we're dealing with people's health and possible of their lives, we want to use a very small significance level. We want to minimize the possibility of a type 1 error to a great extent. So we're going to use our significance level of 0.005, meaning our alpha is 0.005. Now let's set up our H0 and HA so we can at least see what we're talking about. And we're going to try and figure out in the process which tests we're going to use. Now, we've studied 3 different types of tests so far. We've dealt with z-test for mean, t-test for mean, and z-test for proportion. Now, the cool part about kind of listing those 3, nowhere in the problem description did we talk about averages or the mean. So 2 out of 3 tests are kind of ruled out because we're not dealing with means. We're dealing with this many cell phone users developed cancer out of this many, and therefore it's proportion. So we're going to be doing a proportion z-test. Now that we know what type of test we're going to use, let's set up H0 and HA. Test the claim that the cell phone users develop brain cancer at a greater rate than that of non-cell phone users. So we're going to test the proportion against the rate of the brain cancer for non-cell phone users, 0.0340%. Because it's greater than, our claim is an HA. So H0 is the proportion that is less than or equal to 0.00034, because we're changing a percent over to a decimal. And our claim, HA, is the proportion is greater than this 0.00034. All right, let's run our test. We're going to go over to stat, run tests, and we're looking for the 1 prop z-test, so 1 proportion t-test. Number 5, our proportion is going to be the 172 people that developed brain cancer out of the number of people who were in the study. 420,019 people. Our X value is the number of people that developed brain cancer, so 172. Our N, oh, that's not right. Let me change that P0 value. Our P0 value is what we're testing against, so 0.0034. Oop, and I missed 10 to boot. 34. Our X value is the 172. Our N value is 420,019. And our test that we're going to do is the HA of greater than. So let's change this to a greater than. And I'm going to go ahead and draw it. Why not? Let's see the result as well as have it calculate our result. Okay, great. So we have our solution not only drawn, but we do have our calculation as well. Our p-value is 0.0073. Comparing that to our alpha of 0.005, we can see that our p-value is greater than our alpha value. And if our p-value is greater than our alpha, then we can't reject H0. P is greater than alpha, we fail to reject H0. And because we failed to reject H0, that means H0 is good. Meaning the proportion of people who are cell phone users who develop brain cancer versus all cell phone users is less than or equal to non-cell phone users. And therefore, we don't have enough evidence to support our claim that the proportion of people who use cell phone develop brain cancer higher than non-cell phone users. So we'll have to make meaning with this number. It's not enough to get the number. We have to translate that number into a result and a conclusion. So the conclusion would be there is not enough evidence to support the claim that cell phone users develop brain cancer at a greater rate than non-cell phone users. All right, that's it for this one. Until next time, be seeing you. Interpretation of your final results and conclusion can be one of the most difficult part of hypothesis testing. I'm not going to read through this problem, but I am going to grab some very important information, and we'll talk about what would be the appropriate conclusion. A consumer advocate thinks that the assembly time is higher than 14 minutes. That's the claim. Out of that, we can build our HA and H0. So our HA is mu is greater than 14. Our H0 mu is less than or equal to 14. Now I'm even going to give you the test result. The test result is to reject H0. So what would be the appropriate conclusion? If we reject H0, then we're saying mu less than or equal to 14 is not good. But our claim is good. So now let's read through the possible conclusions. The data suggests that the population mean is not significantly higher than 14 at an alpha of 0.01. So there is not enough evidence to conclude that the population mean amount of time to assemble the Meat Man barbecue is higher than 14. Now I've highlighted two specific phrases to really try and have it stand out to you that these two phrases are what's going to change within the possible conclusions that you're going to have to select from. So the first one is not significantly higher than 14 and not enough evidence to conclude. The second one is data suggests the population mean is significantly higher than 14. So there is enough evidence to conclude that the population mean to assemble the Meat Man barbecue is higher than 14. And the last one, the data suggests the population mean is significantly larger than 14 at an alpha of 0.01. So there is enough evidence to conclude that the population mean amount of time to assemble the Meat Man barbecue is equal to 14. Now you're really looking for that language that is meaningful for the test. We know that our claim is that our average is higher than 14 or more than 14 or greater than 14. And because age 0 was rejected, our claim is good. So data suggests that the population mean is not significantly higher than 14. Well, no way. We're saying our claim is good, so it is significantly higher than 14. So we can rule the first one out because that first statement of not significantly higher than 14 just doesn't make sense because we rejected the idea that it was not significantly higher than 14. Now let's talk about enough evidence. Both the second and the third options use the phrase enough evidence to conclude and significantly higher than 14. But ultimately, what was our claim? Our claim, consumer advocates think the assembly time is higher than 14 minutes. The second one says barbecue is higher than 14 minutes, and the third one says barbecue is equal to 14 minutes. So it had nothing to do with, our claim did not have anything to do with being equal to 14 minutes. It had everything to do with higher than 14 minutes. So the second option is the appropriate conclusion for our problem. Really break down those two very special phrases and make sure that it aligns with the problem. We've reached the end of this lesson.